Get a new document. Save changes, yes or no. Name it, yes or no. It's up to you. Go get a motion detector and a little Ziploc bag. Everybody needs one. And then come up here and I'll send you this file. And you won't have to log in this time because I didn't stop. Okay, this is uses high frequency sound to do a radar thing, which basically it sends out a sound signal. It looks for a return signal, and then it says, I know the speed of sound, and so you were gone for 2 seconds, so you must be so far away. It has built into it actually a speed of sound speed, because the speed of sound changes. And I've seen versions of a program to run this where you can actually change the speed of sound because of where you are on the Earth, or if you're on another planet or whatever. But the speed of sound is pretty much, anybody know? Speed of sound, yeah. Say again?
You talking about the actual unit number? 3.0 times 10 to the 8th meters per second.
3.68 times 10 to the, is that what you said?
3.0 times 10 to the 8th.
10 to the 8th, is that meters per second?
Yeah.
Okay. All right. So anyway, it's set up with that. It's got a little head that you can do, so you can sort of set it like this to pick up your car. You could set it like this to pick up your car. And there's also what comes with these is like a tripod mount that you screw in, and then a clamp that you can clamp like onto the side of a table or whatever. But one of the things that you'll need to do is to figure out like what's the best way to pick up your cart. And usually a 3x5 card taped on the end of it helps a lot. It does like metal a lot. So since that, I don't know if that, is that cart metal or plastic? The track.
Metal.
Yeah, so it may be picking up the track unless you get high enough. It sends out a cone of sound, and then it looks for a reflection, but you know, like when you yell your name at the Grand Canyon and it comes back to you? So when this sends out sound, it bounces off everything. It bounces off you and the table and the wall and whatever. So for example, if I wanted to figure out how far it was from here to that wall, I probably couldn't get that information because it'd probably pick up Carol first. So I'd have to move it up higher. And it sort of filters out everything but the strongest return signal in that 1 over r squared. So things that are closer will have a stronger return signal than further away, but so I need to make sure it's positioned. So one of the things the kids will have to do is to make sure that this is picking up the cart and nothing else. So one way to do it is to have it point in the cart and just sort of move back and forth, and is it moving, and does that number make sense? Okay. All right, so on the side there's a couple of holes. This one is for hooking up with a ULI, and we're not going to be doing that. The other side has an I/O, which is for those old antiquated calculators, 84, 83. And then the USB is the one we want to use. So you have 2 cables in your bag. You want to use the USB one. That one end should look pretty familiar to you, like a printer cable. Okay. So the other end of that goes into your calculator, and if you remember, I asked you to open up a new document. Down the bottom is a place for batteries. Long-term storage of these, I take the batteries out, but if you're going to use them like every month or so, then you can probably leave the batteries in. There is a polarity issue there. Okay. And then back here is the place where you could screw it onto a tripod or to the clamp that comes with it. And then here, if you're doing a cart, you want to be switched this side. If you want to do a ball bounce or a walking person, you want to do this. It's really a sensitivity issue. And the way I generally speak to people about it is that if you're going to do carts, just go ahead and switch on the cart. But if you're getting like a lot of bad stuff, switch it the other way and see if that helps out. Okay. There is a manual that comes with this with the certain lessons. It's usually on the CD. And so there's like 5 lessons or so that you can do with this. Okay, so I'm going to go ahead and show you how I'm going to do it with the computer. I could use your cable, but I would have to have a thing that I can't show you right now, but I will in a minute, to adapt that mini USB to a full USB, or I have our principal's printer cable. and this works just as fine because he's not sure how to print anyway. Okay, so just a regular printer cable works for the motion detector. For other probes, though, you'll need that adapter or the Go stuff. So I'm going to plug this in. I'm going to go back to my calculator. I'm done with this, right? So I said open a new document. So I'm thinking house and then new document. I'm challenged, do I want to save this stuff or not? I'll go ahead and say yes, even though I lost that original. I probably should have changed the name. And then obviously you're going to start here with a new notes page, right? You're going to write down, I'm learning how to use the CBR2. This is called the CBR2. If you have any CBR that don't have a 2 on them, you can't do this, okay? Because they don't have that USB. Okay. So now I'm going to put my motion detector into this USB port. And what should happen is that it sees the Go Motion software, which was installed when you installed this program. And then I'm prompted, like, where do you want to see this at? Now, you won't always get this option, but I will show you on the menu how to get this option if it doesn't come up. So it depends on where you're at and how you got there. And this is one of the biggest problems that I've seen that kids have had, is that when they plug it in, they don't get this. And thousands of reasons why it wouldn't happen. But this is a prompt to say, where would you like to see this data? If you just want to see the meter, then you choose the last one. If you wanted to put it in under some app, like I showed you on that PowerPoint, then you could put it in Data and Stat, which is the most popular place. You could put it in List and Spreadsheet, where you don't see a graphical representation of the data, but you see the numbers as they come in, which is the first, when I showed you the ball bounce, that's the first time you saw that ball bounce, and in your mind's eye, did you see that bouncy, 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 or did you see one bounce, or did you think it went up and down? Okay, so there's some advantage to do the other. And then the graphs, which is for chumps, so you don't want to use that. Okay, I've chosen Data and Stat, but I have to tab over to get OK. And this is one thing that people have trouble with the Nspire, is the tab. When you logged in, you put in your stuff, you wanted to tab over to log in. Tab in to, okay. And now that it's highlighted, you see it's highlighted? Then you can press enter, and now it's in List and Spreadsheet. What it does is it automatically sets up to understand that I'm going to take an experiment for about 5 seconds. I'm going to be in meters. It says down here meters, and right now it thinks it sees something 2.834 meters away. What is 2.834 meters away from that motion detector? Okay, so if I believe that's true, I could go stand right here, and now it's saying about a meter. Okay, and remember I said I want to see that wall. Well, it's shooting towards that wall, but it's not high enough. So how far is that wall away?
Okay, now is this like the old one where you have to be at least a half a meter away for it to work?
15 centimeters. This is better. So, but this is a good point. You can't be any closer than 15 centimeters. So when you do your cart and you're measuring the cart coming towards the motion detector, there's no need to keep data after the 15 centimeters, although you're welcome to keep it. It's like that gibberish in the ball bounce is stuff I don't need to look at. Okay, so do you think it's about 10, well, now it's 4, now it's 0. I've been able to get 30 meters out of this baby if you squeeze it right, but of course not in this room. All right? So if I want to know how far it was to Carol, what do you think?
Now, it used to come out as a cone.
It still does, yep. So do you think Carol's 1.8 meters away from me?
No, I think that projected.
Okay, remember the glob is split? You need to have in your mind's eye what 1.8 meters is. And so I'm picking up that projector even though I'm real obviously pointing at Carol. But if I went up higher, okay, and if I went up higher, okay, so I'm getting the camera, right? So it's important for them to relate this number here. Nothing's happening yet, okay, but we are getting readings just whatever every 2 seconds or something. So on this menu, there's some options. So try tabbing, and see what you see when you tab. So when you tab around, you'll see the play button's highlighted. You'll see that this middle piece is highlighted. You'll see the X is highlighted. Very hard. If you hit X, that kills it, and you have to do Control D to bring it back. And then I'm back to the play button. If I go to Menu, I can design the experiment. I can set up the collection, do a new experiment. A new experiment is good to have if somebody set it up and it's like a real bizarre thing. It's like everything seems to be wrong. Just do new experiment, it sort of resets it. If I do a new experiment, then it's all back to the original. And then if you want, you can change the sensor. You can zero it. So what you could do is you could put the cart in its initial position and call that 0. And then when you run the experiment, as the cart comes towards you, you would get numbers that represented its distance from that 0 point. Okay, so if it went one way, it would be positive. If it went the other way, it came closer, it would be negative. Now, but when you zero it, what happens is that somebody else who uses the same calculator or whatever, it may be zeroed at a wrong place. So that's where you do the new experiment. Well, if you zero it, it just remembers it for a while. So if things are like, this is not right, try a new experiment. And then that undoes it. And then you can change your units. And pardon my English, you could do this in feet. Okay. But nobody want to do that. Escape, get rid of everything. If you press play, which you can do by pressing enter, then it collects data. Although I didn't walk in front of it, sorry. And that was the data, I thought it was pointing this way. And that was the data it picked up for the 5 seconds. I could change the 5 seconds to 15 seconds or 10 seconds, but notice that when you press play, in this case it says, do you want to keep this first run or discard it? Since it was really bad, I'll discard it. And then I can stop by pressing enter, and it'll stop it if I didn't need the full 5 seconds. And so this is the kind of graph we're looking for when you do the experiment. Some gibberish, the cars move, and then the car stops. Okay. And so this is the kind of graph I'd like to have. All right, I think that's enough of the set, so let's go ahead and talk about this lesson. So go to House and open up the Conservation of Momentum lesson. Okay, so I go to House, I go to My Documents. I now have a second file. It shouldn't have been that you had to log in again, but maybe something happened where you had to log in again. But as soon as you plugged in, you should have got the stuff. And then you notice that you did get it. And so I will tell you that as you change this, I'll say, no, I don't want to save that old data. You would need to keep your original data involved. I unplugged my motion detector, which you probably should have done too. Okay, so this is a revision of the Conservation of Momentum lesson that Todd Mornstein wrote for y'all. And if you go to the second page, they ask you some questions, and you'll notice that, well, I won't mention that yet. Go ahead and go to the second page and answer the question. So 2 kids are standing on skateboards. The implication is that it's frictionless. Kid 1 weighs 750 newtons, and kid 2 weighs 350 newtons. Are these kids of the real world, or are they just imaginary kids? You think because they're too heavy or too light? If they push against one another, which of those would you think would happen? And then go down and press enter to make it excited. Okay. Now, this one has a tell in that I'm showing the correct answer. And so on the teacher edition, when you write these problems, you have an option to show the right answer on the teacher edition or not. And even if you did choose the one choice, you could hide them so they're not there. Okay, so let me just warn you that if you start this out with your kids, they'll see the correct answer, although you may not have seen it. Okay, and so you would need to decide if you wanted to do that or not. Okay, let's go to the next page. What's on the next page? Again, we're thinking about an experiment we're about to do and how these questions relate to that and the teaks involved. Same question, different answers. This has to do with their velocity. So pick one of those. All right, now we're going to simulate two carts being pushed apart by a force for a specific time period. We're going to model this constant force of a first time by putting some potential energy in there, and then when you press this button, it releases, and that was going to push the cart away. Okay, so this is going to be our mechanism for giving that constant force. The trick is, if you don't get these, and you got other stuff, how will you give that constant force? Okay, and so that's the one thing that you need to think about in terms of bringing this to the children. Okay, I might ask my kids to underline or bold keywords in this document on this page to say what's important, because oftentimes they won't read them. Are the masses the same on both carts?
They both have a little push in them. I mean, you don't have
virtually the same. One has a little release mechanism, the other don't.
Okay, this one doesn't imply that they have the same mass. One has mass 1, and one has mass 2. Sometimes those could be the same, sometimes they're different. It is very difficult to make them both the same, because one of them has the spring mechanism in it, so it's obviously different in weight than the other. And so, but you could add masses to them so they were effectively the same. Now, you believed in your heart that they were how many grams? 500 grams. Is that because you looked on the bottom and it says it's 500 grams, or just because you believe in your heart? Okay. All right. And I know a lot of people with the carts, they do have a piece of tape on the bottom saying how heavy they are before it was dropped the last time, and then every time it's dropped, they reduce that some. But you could make them equal, but that's fairly difficult. All right, and then, okay, then we're going to put the motion detector at the end to measure the distance to one cart. So the question is, do you put the motion detector at this end, or do you put it at this end? And which cart will be picked up by the motion detector, and how well will that happen? That is, how strong a signal will you get? Will you have any problems or whatever? Okay, so that's a logistic thing. And then it says to use the simulation, you click the play button, and then observe the relationship of the two carts and move to the page after the carts. Whatever that means. Okay, so now I know for sure that mass 1 and mass 2 are supposed to be the same. They're 1 unit or whatever that is. They are initiated being together, and the cart, the motion detector is picking up which cart?
1.
Okay, and so it'll see an object moving toward it. All right. What's this DM1 and DM2?
Distance to cart 1 and distance to cart 2.
Okay, so that sort of is supposed to mean where they're touching. But in reality, the motion detector will pick up the rear end. And so this distance here, okay, will be what the motion detector picks up. But this one's picking up where the leading end is. Okay, so that's what that means. This is 1.106 units, okay, to the center of that, and from here to here is point. So one of them is this, and one is the other. So the image is a little different than what you actually will do. But the question is, like, where are they? Okay. So what's F3? Remember the hurricane that took out Oklahoma City? That was an F5. This is the force 3. Remember, the spring is cocked to hold so much. I wonder if you could lighten that up some or make it more. If you could crank it down some to make it a more powerful punch, what would the F be? Okay, so like, okay, so it could be like 4. Or I could loosen it where maybe it just was lighter, and then that would be 3. And then the time is currently 0.2 of a second, because it took me that long to explain it. So go ahead and press your play button and see what happens. Once you press play, it'll go into a pause if you want. So you could pause it if you like. So I'll go ahead and do mine. There's play. And then I can pause it. The distance here is now 3 as opposed to what was it, 0.6 is supposed to be effectively 0. Okay, so it has moved. So the reference here was 0. And so you could actually do that by having the motion detector bounce off a cart or something that was between the two carts and 0 the probe. Okay, and so then at this point, 5 seconds, this cart has moved 3 units over this way, and this cart has moved 3 units over this way. Now, the reason that they're both positive is because they're moving away from the origin. Okay? So the way that things work is that if they come towards the origin, okay, the distances get smaller. And then if somehow they would pass the origin, they would do that. So with the motion detector, if I zeroed this at the place between the two carts, and the cart started to come toward it, then those numbers would be negative. Okay? And then if I zeroed it here and the cart went this way, those would be positive. So the simulation and the actual thing with the motion detector are different in that way. But because they both have the same mass and they both have the same force, what can you say about the velocities of the two carts? They are the same because they travel the same distance in the same time. Okay? Or are they the same in the sense of one of them's negative and the other's positive? So would it be more correct vocabulary to say that the speeds are the same, but the velocities are different? When it's with kinetic energy, I don't care. Okay? The magnitude of the velocity is the same. The speed is the same. The velocities aren't the same given the point of reference, yes, but given with my motion detector, not. Okay. All right, and so I just paused it. How do you reset the animation?
Button to the left of the
Okay. And if you hover over it, it says that. And just for a note, the motion detector was 4 units away from the center. Okay. Now, your point's well taken, and I was going to mention that, and I appreciate you bringing it up, is the 15-centimeter rule. Although the way that the experiment's set up, it doesn't matter if you got garbage on either side. And so basically, the instructions are start the motion detector, spring the carts, and stop the cart before it runs off the table. Okay. So I'll reset it.
Okay, but that simulation, isn't that misleading because you only had that one motion detector? That one detector, those numbers wouldn't be the same.
It depends on, yeah, I mean, it would be nice if there was another motion detector at the other end to imply that that was how far it was based on this being, well, I don't know, even if that way, it's not correct. In that, because if this cart assumes this is 0, and then this starts moving this way, then the number would become smaller than 0. And so it would be a -3.
And also, you can't plug 2 in here, can you?
Not in there, but you can through the computer. But Yeah, the way that we want to do this, I think, is to have one motion detector on one cart and then switch carts of different masses. So if they have the same mass, doesn't matter which carts go into the motion detector. If you make one heavier than the other, what would happen? Well, if the momentum's conserved, MV and MV must be the same, but the M's are different. So you're going to have different V's. And so the way you simulate that with the one motion detector is that you take the heavy cart on the side of the motion detector, and then you repeat it with the lighter cart on the motion detector, and then compare those two. That's the way this has been written. So we can take a look
So
at that.
can you use this with LabQuest or LabQuest or blue, the little aqua green one?
Some of the probes will plug into this, but the software is different.
Okay, so I can't use this with that.
You can use the motion detector with the LabQuest,
Right.
but you can't use the LabQuest with the Inspire because they basically are the same thing. It's like, can I use a HP printer with my HP
And you
printer?
guys just, well, I don't know you guys, but some, like we did the, what's that, Lady Foundations training? And they used the LabQuest. You just sold us on that this summer and last summer.
Well, you can use you can use the LabQuest with the motion detector.
Right, that's what I did.
And so you could do the same experiment with that equipment. And one of the things that y'all need to think about is like, what equipment do I have? And how will I do this experiment? And if I've been successful and had high scores on this TEAX item, doing it the way I was doing it, then I'm not sure you could convince me to change it. But I do need to know how to use this equipment that they've sent me and then think about possibilities. So one of the goals is to have you do stuff with the kids addressing this TEAX and using what we've got. But what we've got may not be perfect. And one of the goals of today is to try to make it like we want it to be. Okay? So, yes, ma'am. Sorry.
Okay, you got all this information that you have actually put out to your students that doing an experiment. Can you collect all this data yourself and put it in your own spreadsheet to show them just one big spreadsheet?
Well, the data that's being collected is not being collected through the simulation, but further on in the document, the simulation will actually collect data for you. And so the kids can do that on their computer. I can do it on the teacher's computer through the simulation. So it's like a Java applet, but the thing that this has that most Java applets don't have is it actually gives you the data. So you can go to a list and spreadsheet and see the numbers. Okay, and that comes later in the document. Okay, good discussion. All right, so did anybody run it past the time that it hit the cart? What happens? Did it just stop after that? Just keep running forever?
It goes back. It'll come back and then it'll restart.
Okay, so in reality, that's not going to happen unless it hits a bumper. And then if it hits a bumper, we have an elastic collision. And, so the advantage of looking at the simulation is only to see what's happening as they move apart. The point being that because they had equal masses, they have equal really? They have equal velocities. Okay, let's go to the next page. Okay, here's another question. If you do control up, what do you see?
All the pages.
Okay. Anything else?
You see which questions you've answered.
Okay.
And if you got them right or not, I guess.
Okay. Yes. So if you answered those first two questions, okay, then if you didn't answer them, you get a circle. If you did answer them, you get either a check or an X. Okay. So this is one version of this document where it's a self-check, so the kids can see that. All right. So we're not going to answer these questions. Page 3.1. Okay. You want 2 carts, and you want to put 50 grams extra on one cart. So go mass your 2 carts real quick. So we need 2 carts of known mass. So you got massed carts, bring them over. Need one with the spring and one without the spring. So you know the masses? Okay, so we're going to use your carts. Okay, somebody write down 512.2 kilograms.
511.2 with the one with the spring.
Okay.
The last one is how much?
512.2,
And mass,
and that's in grams.
and mass 2 is what?
511.2.
Okay, pretty close to being the same.
And then mass 2, you added a 50 grams, right?
Okay, so you want to put 50 grams on this one, or?
We're going to add it to which one?
To 2 is the directions they added to.
Okay.
Okay, So this would be 2. This is the one with the spring. It is cocked. Okay, so we've got these 2 together, and he's going to put his motion detector here.
Do I need to know?
Okay. Okay, so what he's doing is putting the data on this next page. So he put this in here, okay? And then he's got his motion detector at the end. Now, he's plugged his motion detector in, but did you have that bar at the bottom? Or he's not? Okay, so when he plugs the motion detector in, it pops up just right here. Okay, now sometimes that won't happen, but on the menu there's an option that says display data in the current page. Okay? So how far is the first cart? Okay, and so if I move it, is it still a half a meter?
4/10 of a meter.
And if I move it, so I'm just trying to make sure I'm picking up the cart.
Okay.
All right?
About half a meter.
Okay, so he's got the cart. All right, so what he's going to do is press play, which is just enter, and release the hounds. Okay, so tell me when you press play.
Fresh.
Now release the hounds. You only got 5 seconds, so. Okay. Make sure the motion detector doesn't get hit by the cart.
Okay. How do you stop that?
Throw a small child. Okay, and so now he's got the data in his calculator. So y'all come around and look at his calculator for a second. So he's going to go to the next page. Control right if you want. He wants to use his pointer. And then the next page. Next page. All right. So here's his data. Do you see you see when I said you only got 5 seconds? Okay, but that's supposed to be a straight line. We put a movable line up there and get the slope of that line. The slope of that line will be meters per second, which is what? Velocity. I know the mass, so can I not calculate? Okay. Run it again. Switch the cars, the heavier ones on this side. Doesn't matter how close it is. Doesn't matter. I mean, it matters in the 15 centimeter sense, but if you start about the same, it doesn't matter. Doesn't matter how quick you do it, but you want to do it before the 5 seconds is up. And this is a little steep, but straight as Dickens. Okay, so I don't think I'd have any problem getting the name of that line. Okay, now what we need you to do is to think about this and share with your leaders. Like, what would I do? How would I do this? What teaks is it? Somebody told me it's 6
It's 6C and 6D.
6C and 6D, so go look at that, and thank you very much.